Boa tarde a todos e todas. Primeiramente, pedir desculpas por ter um acidente na Brasília, uma ambulância atravessada, e aí a gente levou mais tempo do que o previsto, né? Mas ainda em tempo para iniciar a apresentação aqui dos meus convidados, que vêm dos Estados Unidos. Como é um seminário internacional, vou ver se eu não sei se tem alguém de fora do país assistindo pelo canal do YouTube, está sendo transmitido, então talvez eu fale um pouquinho também, eu introduzo um pouco em inglês, né? Mas eu vou introduzir aqui o primeiro palestrante, e em seguida eu vou falar do nosso segundo palestrante nesse ínterim, né? E basicamente esse é um encontro, um momento, né, para a gente falar um pouco sobre essa temática de ritmo circadiano, de ritmo biológico, particularmente aplicado ao contexto clínico, né? É por isso que ele está ocorrendo também dentro do canal da universidade. E aí, obviamente, as apresentações vão ser em inglês, mas se vocês precisarem, né, de uma interlocução, se vocês quiserem fazer perguntas, pode ajudar, certo? A estabelecer essa comunicação com a plateia aqui presente, ou quem estiver assistindo também pelo canal do YouTube, né? Haverá um chat, né? Uma oportunidade de colocar perguntas, e ao final das apresentações a gente pode resgatar essas perguntas ou comentários, tá certo? E trazer aqui para os nossos convidados, tá certo? Sem demorar mais, né? Eu vou apresentar o Mark Rubin, que é pós-doc no laboratório do professor John Moganesh, do Children's Hospital Medical Center, o Hospital Pediátrico de Cincinnati, em Ohio, que é um hospital de referência, não só nos Estados Unidos, mas internacionalmente, recebe pacientes, né, e pesquisadores e médicos do mundo todo, né, e ele é um grupo que trabalha com ritmo biológico aplicado à medicina. E o Mark, ele estuda, né, ritmo biológico já há um tempo, começou com drosófila, com mosca, tem PhD na área de neurociência na New York University, né, mas também trabalhou na indústria, então trabalhou na indústria farmacêutica. Então tem experiência também nesse campo de indústria, né, de inovação, né, e já há um bom tempo trabalha com ritmos biológicos e mais recentemente tem desenvolvido pesquisas importantes com análise de dados, data analysis, né? E vai trazer para a gente aqui algumas dessas análises e aplicabilidades na área clínica, certo? So, for whom who are watching through the internet, if you have any question, please just text the chat that we can get the comments or answers later. That's it. So, Mark, please, and thank you.
Thank you, Tiago. I'm just going to, can you hear me okay? I can talk a little bit louder. Thanks, Tiago. I only understood Drosophila data analysis, but and I'm also about Drosophila. So it's really nice to be here and have the chance to talk about ways we're studying the role of science in medicine. And one aspect of medicine relates to outcome treatment. And there's actually a history of trials, clinical trials.
Better? Okay.
There's a history of trials comparing the effects of medicine taken at different times of day. And we've identified 84. They test many of the most prescribed drugs in the world. And so, as a circadian biologist who works in a clinical setting in Cincinnati, I've been very interested in trying to learn from these data as much as possible. And so I promise a proper introduction to circadian biology is upcoming in a few slides. But I thought I'd open up by trying to convey a sense of what we actually know from patients about the impact of medication timing. And to get at this, we computed an effect score for each of the 475 reported outcomes from all of those 84 trials that I just mentioned. And nearly all of those trials compared treatment in the morning versus treatment in the evening. And our measure of effect is SMD, for standardized mean difference. And this is nothing fancy at all. This is just the average difference in outcomes between evening and morning treatment. And so values here above 0, treatment was favorable when given in the evening. Values below 0 here, more favorable when the drug was given in the morning. And so what can we say by sort of looking at this plot of a lot of data points? Well, for one, lipid-lowering drugs, specifically simvastatin, were consistently more effective when taken in the evening. And this is actually not new knowledge at all. Statin drugs work by inhibiting the key enzyme in cholesterol synthesis, and daily variation in levels of that particular enzyme, we've known about them for a long time, first described some 50 years ago. And that seeded the idea that it may be beneficial to time cholesterol-lowering therapy with the time of maximal abundance of its target. And indeed, in trials, short-acting statin drugs were shown to be more effective if taken at bedtime. And if you read the FDA labeling in the US, it recommends once a day in the evening. And so simvastatin, I think, is actually a really good example of medication timing in practice, where we know something about the mechanism for the timing effect. A second observation we made is that low-dose aspirin seems more effective as an anticoagulant if taken in the evening. But unlike simvastatin, this is neither currently common knowledge, this is not common practice. In fact, for the millions of patients, many millions of patients who regularly take low-dose aspirin for the secondary prevention of heart disease, it's actually normal to take the drug in the morning, not the evening. And so there are some ideas about why it might work better in the evening, but I think it's fair to say we don't really know. And so a third observation from all of these trials is that we actually can't, at this point, say a whole lot more with much confidence. So there's plenty of suggestions that in all of these data that timing may matter, but there's actually very little replication. And even in cases where there is replication, there are opposite conclusions, as in hypothyroidism here. And so I think that it's fair to say, despite 50 years of these kinds of randomized trials, there's clearly lots that we don't know about how timing may matter in practice. And I'm going to talk about how we've been approaching this question, what we're learning, and where we're hoping to take things. But first, as I promised, some background on circadian systems, which starts, believe it or not, with Twitter. Sorry, this was a lockdown hobby of mine. So this in red is 5 years of my Twitter, the social media platform Twitter, 5 years of my use compressed onto a 24-hour clock. So you can learn a lot about me really quickly here. I tend to sort of get going at 9 a.m. I've kind of reached a steady state by noon. I'm like, tweeting along. And then there's a dip in use that actually corresponds to my family when I eat dinner with my family. And then I kind of, Twitter use ramps up again, and I'm pretty wild around midnight, and then it starts declining, and then it's completely quiet, thankfully, by 3 a.m. And so it's really a picture of when I tend to sleep, when I wake, when I socialize, when I eat. I mean, there's a lot that this simple curve describes. Of course, different people keep different schedules, like this person I know in blue. And there's a lot of interest in terms of research about, hey, which one of these schedules might be healthier? I think that's interesting. We can talk about that, but that's a pretty complex question. I just want to make a simpler point here that rhythms are really a feature of everyday life functions, and that these rhythms have a cellular basis to them. And so here I'm depicting kind of the bare bones mammalian version. But this is a basic feedback loop architecture that is deeply conserved throughout evolution. And so you have transcriptional activators regulate the expression of repressors. which are translated, form a complex together, move back to the nucleus, and repress the activators, and thus repress their own transcription. These repressors eventually degrade, and you get a new cycle of activation. And so this loop here takes about 24 hours to close, and it really is the essential kind of molecular ticking of the clock. And it confers rhythmicity to many, many output genes, which I'll return to this idea. So it's great to have an oscillator mechanism in cells, but it's got to be able to be synchronized by something that's meaningful, some meaningful cue. And so light, it surprises nobody, is the major synchronizing cue for the central clock in the brain, which is a group of about 20,000 clock-containing neurons in this tiny region of the hypothalamus referred to as the SCN. And neurons here receive light cues from the visual system. They're able to align their clocks with the solar cycles and then download that time of day information to other clocks, to synchronize other clocks throughout the body. And it turns out these other clocks are virtually everywhere in humans and in other organisms. And virtually every cell type studied expresses clock genes and has the capacity to generate 24-hour oscillations that I just described. And what's more is that while light is a very important synchronizing cue to clocks, it isn't the only one. So clocks in the liver can shift in response to our dietary intake. There's quite a bit of evidence that an research of Dave's is that lung tissue and lung clocks are sensitive to the amount of oxygen they receive. And there are many other examples here. And so the idea is that what emerges in health, at least, is this kind of concert of 24-hour rhythms in physiology, immune, endocrine, cardiometabolic processes are all tightly tuned to time of day. And, again, of course, depending on the person, you can turn the dial here one way or the other. You now know I'm not in my deepest sleep at 2 a.m. But the takeaway is that rhythms in physiology are pervasive. And I don't know if you can study a system without some time of day component to it. From mice, where multi-tissue time series gene expression studies have been possible, we're gaining a sense of the extensive transcriptional dynamics that set up these rhythms in physiology. And we're also gaining a sense from these studies in mice, of all of the ways in which time of day may impact human health. And with genes involved in disease, genes that are targets of drugs. But of course, mice are not humans. And I joined the Hoganish lab to try and contribute to studies of 24-hour gene regulation in humans. And I think that I got very lucky in my timing. The lab had just released the first iteration of something called Cyclops. This is an algorithm a machine learning-based algorithm for estimating rhythmic transcription that does not require the serial time sampling done every few hours, over several days. And Cyclops is, I'm not going to have time to get into it. I can talk offline, if anyone's interested in kind of the algorithmic part, but it really essentially works by taking advantage of particular phase relationships between clock genes to estimate how samples are ordered around 24 hours relative to each other. And the big advantage here is this allows us to detect rhythmic genes from any collection of samples we have, whether we have any information on collection time or not, we can infer that. And that leads to my second bit of luck, I think. So the GTAX project had just released, this is a publicly available repository, had just released RNA-seq data from many different tissue types, from hundreds of human donors. And it was a really good use case for Cyclops because no time of collection data was available. And so we made a few tweaks to the original Cyclops algorithm that I'm not going to kind of gloss over. But we were using Cyclops. We were able to estimate rhythms in expression for these 13 different tissues. And I always say the numbers of cycling genes is not something to get hung up on. That's just a matter of where one's statistical cutoff is. But after saying that, if we sort of bound the false discovery rate at 5%, and we randomly sample increasing numbers of tissues, the number of rhythmically expressed genes kind of starts to level off here at about half of the analyzed genome. So about 50% so lots of cycling things. If we look at the distribution of robustness for all the cycling genes in each tissue, the known clock genes, which I've colored red here, they tend to stand out as the most strongly rhythmic genes. And so again, these are deeply evolutionary considered genes that are kind of what we think of as the core clock. And presumably all these other gray balls here are sort of the output rhythmic genes. And apart from the clock genes, there is a lot of tissue specificity. And like I said, that specificity in terms of gene identities, also in terms of the phase profiles. And so it's common to see these sort of peaks of transcription around the inferred transitions from inactivity to activity. But it isn't universal. There's some bimodal tissues. Presumably, this is all about enacting the right biology at the right time in the right space. So I mentioned earlier that statin drugs target a gene whose expression cycles throughout the day. Here we now have a list of hundreds of additional cycling genes that map to known drug targets, drug metabolizing enzymes, drug transporters. And so how do we move from gene lists to clinical evidence? Well, one approach is to try and use the data that's already available. And our hospital in Cincinnati alone, in just 1 year, generates digital medical records on millions of patients. And so obviously this is orders of magnitude more than all of the participants of all of the 84 randomized trials that I spoke about at the beginning. So our question was, well, can we use these data to evaluate predictions for select indications? And we first looked at a drug called hydralazine that's indicated for hypertensive crisis. And we chose hydralazine for a few reasons. Hydralazine is metabolized in the liver by two enzymes. It's actually an actionable pharmacogenetic. These two enzymes are actionable pharmacogenetic markers. And so these two metabolizing enzymes were also rhythmic in the liver in our analysis. And so this drug is a vasodilator. It's used acutely in hypertensive crisis. And the drug has a very short half-life. It's in and out of the system pretty quickly. So our reasoning was that, well, if the abundances of this NAT enzyme varies by time, then hydralazine availability, and possibly its effect, would also vary by time. And so we analyzed responses to thousands of doses of hydralazine given over several years at our hospital. And so here on the x-axis is the time that the drug was given. On the y-axis is the median response, or percent change in blood pressure. So more negative, a greater response to the drug. Diastolic blood pressure, DBP, and systolic blood pressure on the right here. And so there's this kind of clear bimodal pattern to the response, with sort of larger average drops in blood pressure in the middle of the night and the middle of the day. And if we kind of look at the extremes, it's about a 4% greater effect with midnight dosing compared to kind of the least responsive time, early morning. And so this is not a project endpoint. Rather, we think of this as sort of data that can help us identify the next questions that we might want to ask. And so, for example, with hydralazine, the NAT alleles are pharmacogenetic markers, as I said. So do genetics and time interact in a clinically important way on drug exposure? We don't know. If we turn to an animal model, do we see the same drug-taking effects? And if we do, what happens under circadian disruption or sleep disruption? So these are kind of follow-on questions we're interested in. It may be less obvious, at least it was to me at the outset of this project, but EMR data, electronic medical records data, above everything is describing the healthcare process. And that's probably not something to ignore. For example, with hydralazine, the decision to treat, actually this is for any drug, the decision to treat involves an order is placed in the hospital and then a dose is given. These are two separate sort of time-stamped events. And it's obvious here that neither of these are uniformly distributed around the clock. There's this lull, overnight lull in orders placed, and then a morning rise with this particularly sort of distinct surge in orders placed between 8 and 10 a.m. And that pattern is not unique to hydralazine. So we looked at over 100,000 orders and doses of 12 very different types of drugs in the hospital. And again, we had that sort of overnight lull with this sort of morning 8 a.m. Surge in orders placed. And so there are these kind of treatment rush hours, if you like. And this period of of maximal treatment corresponds to clinical rounding times. And so this is a time when the patient is seen by the full clinical team. A lot of decisions are made. I know nothing about hospital procedure in Brazil, but I suspect something similar may occur. And depending on the drug, this actually may not be ideal. When we go back to hydralazine, dosing is least likely to occur for these operational reasons in this overnight window, which is when the patients were on average most responsive to the drug. And so I'm not a clinician, but perhaps as we build our knowledge and learn more about biological rhythms, it also be an opportunity to sort of rethink some of the traditional operational patterns. And so I've been talking mostly about treatment. We're also interested in applying the electronic medical records data to questions about timing and other aspects of medicine. One of these is looking at seasonal patterns in emergency vision. And so, of course, we know that many infectious diseases and allergies are, of course, seasonal. I got interested by the observation that more than half of all diagnoses, as captured by the ICD-10 codes from the health record, vary by month and year. And so this particular analysis draws from about 100,000 admissions to our emergency department over a 10-year period. And you can see that 5 clusters do a reasonably good job of capturing the different states here. There's this sort of winter peaking cluster, early spring cluster, diagnoses that tend to be high in the summer, sort of spring and fall peaking cluster, and then this sort of, I guess you're able to see my cursor, this sort of fall only cluster. And then we can ask, well, are clusters marked by particular disease areas? And so, for example, cluster 2 here is bright red, meaning that it has twice as many behavioral health-related codes than you'd expect by chance. Clusters 5 and clusters 4 are also enriched for these psychiatric mental behavioral health-related codes. On the other hand, clusters 3 and clusters 1 are enriched for respiratory and infectious sorts of diagnoses. And so there's probably some more information in this map as well, I think, but I'm going to jump to looking at a few examples. And so at the top there, we get really clear pictures of RSV, infection, and asthma crisis in Cincinnati's four-season geography. And then some curves from mental health. And so suicide ideation and impulse control, each with apparent seasonality. They have different shapes. And so, but of course, at this point, I always point out, it's important to keep in mind that patients are maybe never describable by a single ICD-10 code. Most of these patients are discharged with multiple ICD-10 codes. And so we ask, well, can we get more insight? And so I'm just focusing on the matrix kind of on the top right there, where it says admin vectors. Can we get more insight into seasonality if we were to view sort of each admit not as a single ICD-10 code, but rather as a vector of values along features? And so this is just a very simple matrix. Each admits are in rows, features are in columns here. So you have a 0 or a 1, denoting either absence or presence of that particular diagnosis in that particular patient. And our goal here is to use these vectors features to cluster patients that are similar, have sort of similar diagnostic profiles. I've also had demographic, age, and sex. And I'm going to skip, for the interest of time here, the algorithmic details. I'm happy to talk about them if anybody's interested. To take you to where we settled on 30 different clusters of admits. And so here, and this is a community that, so here each row reports on one cluster. And so that we have information on the total number of admits or patients in that cluster, some information on sex and age makeup, and then the ICD-10 makeup by way of this heat map. And so in this heat map, each column is a distinct diagnosis or ICD-10 code. ICD-10s that are colored red are enriched in that cluster. ICD-10s that are colored blue are depleted in that cluster. And I haven't labeled the specific ICD-10 codes yet, but you can just by paying attention to the disease area code over here, convey some overall structure. So there are multiple clusters that are enriched for mental and behavioral health related diagnoses, colored gold up top. There's kind of separate clusters here in the middle that are enriched for in the respiratory space, colored yellow. But we can pull out individual clusters to get a closer look and to evaluate seasonality, which was our point for doing all this in the first place. And so here's an example cluster that is marked by depressive disorder, ADHD, and high body mass index. Admits here are adolescent, tend to be female, and with a monthly admissions profile that is clearly nonlinear. So there's a sort of pattern here that's defined by a June and July low, followed quickly by the sort of peak in September and October. We don't know what the cause of this is, but surely, so for most adolescents, at least in the U.S., this low period is when they are out of school. This is summer break in the U.S. And then this peak in admission here is the time of return to school following summer break. Here's another cluster. This one's marked by respiratory infection of a few different pathogenic origins. The admits are mostly infants and toddlers. The admissions follow this very characteristic U-shaped profile. And this is well appreciated. It coincides with viral prevalence relative to months in the US. And so this is not surprising. It's something of a positive control for the approach here. Here's a cluster that's defined by diabetic crisis, predominantly adolescent. There's definitely more complex sort of seasonal variation here. We don't know why. We're interested in understanding it better. And one idea that's proposed by an endocrinologist at Children's is that this September peak here actually may relate to non-compliance with insulin treatment that is associated with the return to school. And in fact, one of the diagnostic codes that turns out as enriched, this was also unsupervised, is non-compliance with medical treatment. But we really don't know. It's just ideas of what might be causing these seasonal shapes. So there are other clusters that I don't have time to go through. But for anyone who's interested, I'd love to share our data. We, of course, like to understand, how these different extrinsic factors come together to shape the patterns we're seeing. One way to do this is, of course, to partner with friends from different latitudes, like Brazil, where these factors would have different monthly profiles, and so I think there's a lot we can learn. Do we have 5 or 10 more minutes? Okay, cool. So for this remaining time I've got here, I'm going to shift to another project looking at clinical labs. And so clinical labs are, of course, hallmarks of organ function and patient health. They guide all sorts of medical decisions. They're ordered in millions per year in any major hospital. And we are interested in a simple question, which is whether time of sampling influences the result in any way. And our data set here is all 4 million lab tests taken in our hospital's ICU over a multi-year period. And of course, there are hundreds of different analytes that can and are tested for. I'm going to focus on the 100 or so most commonly tested analytes in the upper kind of right quadrant here. And the first thing to appreciate in the orange box here is the unevenness of testing for 24 hours. And so there's this obviously very big peak in test taken at 4 a.m. And I've learned this is common practice. At least it is common practice in the US. The idea is that tests tend to be taken at 4 a.m. so that the result can be in hand for morning rounding, whenever that happens, 8 a.m. And so parenthetically, this may not be great for patients' sleep, those who need to be awoken at 4 a.m. for blood work, not all would. But I'm not going to talk about that aspect of it. There's something else to see here that's interesting. There's also what looks to be a 4 p.m. peak in testing. So what's going on? Well, here's a timeline from a single ICU event. And each bar here is one lab test taken. It's actually a metabolic panel, but it's one blood draw. And there are 2 things to notice here. The first is that the frequency of testing goes from this sort of high frequency state to a low frequency state as this patient gets close to discharge from the ICU. So that's sensible. The second thing to notice is that I've indicated in the legend here the time that each lab test was taken. So 4 a.m. is a black ball, 4 p.m. is a gold or yellow ball. And what is obvious is that 4 p.m. tests, the yellow circles, are only happen during this sort of higher frequency testing state. And we can be more specific about that and actually assign a frequency state to each lab test by sort of sliding along, writing some code to slide along the timeline. And you see here the tests for this particular advent fell to one of 4 states. Twice daily testing, once daily testing, and then every other day. Undefined usually just refers to sort of boundaries between states, and we tend to ignore that data. But if we look at the taken times here, again, you start to sort of see what's happening. 4 a.m. it seems to be routine, regardless of the frequency state. And then a 4 p.m. test is added for patients who are getting more than 1 test a day. And so this logic or this pattern of care, operational rhythm, holds up when we look not just that was one advent, this is all hundreds of thousands of advents. Again, we only see these 4 p.m. tests when advents are being tested for more than once daily. So it's then speculated that the 4 p.m. tests would be enriched for sicker, more turbulent sort of health states. And so we can test that. And so the y-axis here indicates the fraction of abnormal tests by frequency state. And so abnormal here is defined as outside of the age-adjusted reference range for that particular analyte. And it seems pretty clear that tests taken from higher frequency states are more likely to be abnormal. And this isn't particularly surprising. In fact, it's intuitive, but what it means is that tests taken at 4 p.m. are also much more likely, substantially more likely to be abnormal. And so that's purely due to bias introduced by the care process. And so any computational effort, and no matter how fancy machine learning or not, that tries to learn something about biology is going to be if it isn't equipped with some understanding of the care process here. And so I think that's a really important point, and one that I harp on. The good news, though, is that with some understanding of these causal pathways, you can better isolate the biological question of interest, which for us was, does test power impact test result directly? And so without going into any model specifics here, after adjusting for all of this, we found that about 1/3 of the analytes we tested show sampling power dependencies. And so put another way, so the analytes at the far right side and the far left side of this plot, the time of day may actually be clinically informative. For example, so this is blood urea nitrogen. Its levels are higher at 4 a.m. than 4 p.m. to the extent that 4 a.m. tests are about 5% more likely to be flagged as abnormally high at 4 p.m. and about 2% less likely to be flagged as abnormally low compared to 4 p.m. And so overall, this is about a 7% difference in the prevalence of abnormal based on the time of blood draw alone. And so there's lots for us, no doubt, to do. But we think this may lead to has the potential to lead to improved understanding of normative ranges. And as a corollary of that, I think that this is maybe sort of foundational to understand which rhythms are retained in disease and which are lost, and what are the consequences in terms of outcomes of that. I think having high-level population-level knowledge is a really good place to start. And I think there are also implications for optimizing medication timing. And then I also think there's implications for understanding costs. Why is blood urea nitrogen higher at 4 p.m.? I don't know. And so with that, I hope I've conveyed a little bit of a sense. I'm sorry if I was kind of rushed or if I spoke too quickly. I'm happy to take any questions later on, or always available afterwards or email. And so yeah, this is some of the ways we're approaching this question here at the top. And I think it's super exciting because I think there's so much to learn in this area. There's so much that we don't know. With that, again, I'm a postdoc in John Hoganish's lab, so always a big thanks to John and to everyone else in the lab. And it's a great group. Actually, Tiago used to be in this picture, so he was a visiting professor a few years ago. It took me a while, but I just removed his picture a while ago, but that's when I met him, and it was awesome meeting Tiago, and I lived this, so I'm very appreciative of that. So that's it. Thank you. I'm happy to answer any questions now. Sorry.
Se vocês tiverem alguma pergunta que quiserem fazer agora, podem fazer. A gente depois dá sequência com a apresentação do David. E pode ser em português, a gente traduz.
A minha pergunta seria se é tão importante o ciclo circadiano e as drogas interferem em termos no time da biologia do paciente. Então, por que o ciclo não leva em consideração o ciclo circadiano se esse PhD tem essa preocupação de ajustar o ciclo circadiano nas bulas das medicações? Entendeu? Então, uma dúvida, o paciente é diabético. Se melhorar a civastatina, tem uma dislipidemia, melhorar a civastatina no finalzinho da tarde. E aí, por que não fazer isso nas duas para poder orientar? A ciência é tão importante, tem que ter.
So basically, the question is about how the FDA, for example, deals with it, and if it's so important, why it's not incorporated in the prescriptions and the information about this drug. So that was about the FDA.
Yeah,
how FDA thinks about that.
Yeah, that's a good question. That's a really good question, and it's a long conversation maybe. But actually, so I think that a couple of things come to mind. One is that that question actually inspired me to do the meta-analysis on the clinical evidence. And it was that question because it seems somewhat baffling to me too. So I think it's a combination. There is not, the evidence is not inscrutable. And so there's lots of mixed evidence. There's for any one drug and disease, maybe there's 2 or 3 trials, and it's not, and the trials are often done in an imperfect way. So first, 2 time points, morning versus evening. Well, this is not the best way. This is not how if we're doing a time series gene expression study, we're not just doing 2 time points, because you can actually, if you have a sinusoidal curve, you can, if you just do 2 time points, you can hit the same sort of level. So you actually, in these time series experiments, you want to do multiple time points to understand the truth. So trial design is problematic, but convincing the drug developer to do multiple time points is a hard battle because it's very expensive. They don't want to test 4 time points, and so they've got to be convinced that there's going to be some return to that investment. And so the other issue is that you need to really understand each individual participant or patient's internal circadian time to know that if you're telling everyone in experimental arm 1, take your drugs at 8 a.m. and experimental arm 2, take your drugs at 8 p.m. Well, 8 a.m. is not the same. Right now, probably in this room, our clocks are slightly different. I know Dave and who knows where our clocks are, because we were awake for 24 hours for traveling, and then I slept for 14 hours last night. So my internal circadian clock is probably nothing to do with the clock on the wall. And so this is a consideration in doing the clinical trials that is actually non-trivial. There are ways to, but a lot of the trials did not factor in any way a person's internal circadian time. So that's something we as experimenters think about. So, and there's a whole bunch of other reasons, but we were talking about this at lunch, and it seems like it's a good these are good trials for universities to run, and maybe more than drug companies, because I think the drug companies they don't like the idea of investing in a 3,000 person study that's going to be 8 time points. Just doesn't sound very appetizing.
Livia is a doctor here, it's a sleep doctor.
Se coletam novos dados ou se trabalham analisando dados já coletados por serviços específicos, e se eles estão trabalhando com dados assinados, ou se eles têm colaboração com outros centros dos Estados Unidos ou não.
The question is if you work only with recorded data, or if you're planning to do, or if you do a longitudinal research, sampling, for example, in terms of clinical stuff. And if you have collaborations in other centers, in the United States and other countries.
Yeah, awesome question. So I'm not a clinician. I'm a circadian biologist and also kind of a computational biologist. And so my personal sort of interest is trying to learn as much as possible from recorded information. But ultimately, I think that the idea is to derive clinical evidence that would provoke a controlled trial, prospective randomized controlled trials. And so Dave, who's going to talk next, is the sleep medicine doctor. here. So those are the kinds of things we can think about doing at our hospital. And so I guess I'm more about, my role is to build evidence using the data that's already existing. But even for that, I think there's a lot of value in having collaborations with other institutes, because some of the predictions we make, through data analysis, some of it generalizes, may generalize to other types of hospitals and other institutes and other geographies. Some of it may not. So actually, Tiago and I have talked a lot about establishing some kind of collaboration here. Currently, we collaborate with Harvard University, so they have 3 large hospitals, and I'm working on looking at the effect of medication timing with the group there. We collaborate, so within our own hospital, there's multiple clinical groups with sort of different focuses that we sort of work with, clinical groups that I work with. But I think it's the more we can collaborate, absolutely the better, even for the computational work that's on data that's already been put, the observational studies. Mais uma questão?
A pergunta é sobre os resultados 4 AM e 4 PM, se tem alguma correlação com o relativo, se foi observado isso de alguma forma. So I'd like to ask if, about the 4 AM and 4 PM situation, if there was anything to do with the chronotype, was it
That's awesome. I don't know. Mark, you have a microphone?
If it works.
That's a great question. Does 4 AM or 4 PM, what's going on with the individual patient's chronotype? I have no idea. I don't have an easy way to evaluate that. One of the huge observational data sets they have power because they're so big. There's a lot you can't easily learn. And in the hospital, so these are also children. So I don't know, and sleep is not recorded as a routine practice in the ICU where that data came from. So I don't really have a way. That would be a case for a random, for a prospective study where you can gather some information on the person's chronotype. You could actually, maybe you could infer that from 24-hour monitoring of blood pressure or heart rate, or you could sort of do it, and maybe a person's stated preference. Are they morning or evening person? And then, sort of overlay, or then evaluate, well, how does that impact lab values? I just, 4 AM, 4 PM, and assuming that both of those times are a mix of all of those variables, but I don't have a way to know. It's a great question.
Mark, can you turn on? So I have one, maybe a pragmatic question. It has been 3 years you published the study in Children's Hospital, 2 years. So since then, what were the consequences? What were the impact in your environment, clinical environment, maybe in other hospitals? Do you have any feedback?
I think data is
the best person.
Probably better on the clinical side because I think you're referring to the study with
the rotating shift and the neutrality.
Yeah.
That's great. We are having some issues with the quality of the slides on the YouTube translation. But
Professor, o senhor pode baixar o slide dele aqui, e ele vai passando lá tranquilo, eu vou passando para o pessoal aqui.
O telefone dele, aí chega no USB aqui. Pode conectar.
Política de segurança do hospital.
Presentation.
Smart. Well, I would have to. I have a university email, so I could try to get. I mean, I'd have to get it on my computer.
Isso no tempo, né? Não tem tempo. We don't have time, that's right.
Yeah, we're getting late.
Yeah.
Alternatively, we can do the talk and then we can upload the slides later.
Acho que vai ser esse caminho, que é fazer a apresentação e depois disponibiliza.
Ok.
So you can share it?
Yeah. Oh yeah.
Continua transmitindo.
Então, vamos continuar aqui nosso seminário, né? Só para quem está assistindo de fora, a gente tem uma dificuldade operacional de fazer isso rapidamente nesse momento, então o que a gente vai fazer é para a sequência na apresentação e o Mark e o David vão disponibilizar os slides na sequência para quem tiver interesse, né? Então, vão estar disponíveis. Então, a gente vai dar sequência aqui com a apresentação do David Smith, que é médico, otorrinolaringologista, pediátrico e médico do sono, né? Tem foco do David, né? Diagnóstico e tratamento de distúrbios das vias aéreas superiores e inferiores, né? Apneia obstrutiva do sono complexa e persistente de distúrbios circadianos do sono complexos em crianças. A pesquisa clínica também, então ele não só médico, mas também pesquisador clínico, especialmente da OS, né? No laboratório, concentra estudos de mecanismos moleculares para progressão de sequelas clínicas associadas a estudo de vias aéreas obstrutivas, usando o modelo murino de hipóxia intermitente. Tem experiência com o estudo da desregulação do relógio circadiano e fatores induzíveis à hipóxia. Também coordenou uma grande equipe multidisciplinar dedicada à pesquisa clínica, translacional e científica para focada em estudos relacionados ao sono, e atuando como diretor clínico do Centro de Medicina Circadiana do Children's Hospital. Né? E tem essa experiência, né? As pesquisas permitem traduzir esse conhecimento em descobertas que podem ser aplicadas a tratamento, diagnóstico e tratamento de doenças humanas. Né? Então, eu vou dar a palavra aqui para o Dr. Smith.
Okay, thank you. That was a really long introduction. I'm not sure what he said. I don't know if I deserve all of that. First, thank you very much for having Mark and I here today to talk about something that I find very interesting and I'm passionate about. So I'm an otorhinolaryngologist and an neck surgeon. I'm also a sleep medicine doctor, and I have a lab. I do basic science research. I'm very interested in obstructive sleep apnea. I'm not going to talk about sleep apnea at all. But I want to talk about basically what we do, why we're interested in this, and then, of course, as a clinician, I want to talk about why I think this is important for patients. And there are a lot of different aspects. I have a lot of slides that are sort of overlapping with Dr. Rubin's. I'm going to skip some of those just for the sake of time because I need to be done in 30 minutes. The last part of my slides are really talking about what we do in the hospital with patients, how we've implemented some of these circadian medicine, or whatever circadian medicine is, how we actually apply this to patient care, because I think ultimately that's my sort of end endeavor. So I don't want to spend a lot of time on this, but circadian biology is an old field in the sense that, it's under the 60s, looking at behavior of flies. As a behavioral geneticist, we wanted to know why flies had different patterns of activity, and that really was the beginning of a very complex field called circadian biology. And I don't want to reiterate what the molecular clock is necessarily, but we know now that the clock, even though it's in all of our cells, its transcription and translation, how genes are expressed, that it really dictates a lot of what we do in a 24-hour period, right? So when we're most likely to have the best exercise, when we have the best sleep, when we go to the bathroom, these are all things that are sort of driven by our internal clock. And so sleep, we think of sleep as the clock. Sleep is a representation of what the clock is doing in our brain and our body, but it is not all-encompassing of the fluid. A prime example, blood pressure. Everyone here probably knows that our blood pressure has peaks and troughs throughout the day. Every day we have patterns. And in fact, if you have a blood pressure that does not have peaks, it does not have troughs. Like, for example, non-dipping. I don't know if you've heard of non-dipping, but non-dipping blood pressure means that your blood pressure does not drop at night when you're asleep. And if it doesn't do that, that is an equivalent cardiovascular risk and can predispose you to having heart attacks. So even though we try to treat patients with hypertension, we should also be looking at other features of blood pressure like non-dipping. Most places don't, but there are a few places that are doing trials to actually look at non-dipping and how we can treat it. Even if you have normal blood pressure, if it doesn't drop at night, that in and of itself is a risk factor. And so, as a clinician, we know that, yes, light and dark are factors for the clock, but lots of other things influence your internal clock. Exercise, for example, body temperature, feeding. When I talk to patients that are phase delayed, for example, and I find out that they eat dinner at 9 o'clock at night, that actually predisposes you to being what we call a phase delay or a night owl. That is an extreme night owl. And we know that our internal clocks are influenced by a lot of different things. Disease, for example, age. As we age, we think that our clock probably isn't as strong, which is why we have changes in our sleep patterns as we get older. Hormonal changes, for example, in kids, we often have to consider the age that a child presents to our clinics to try to figure out how we treat them. And then, of course, external factors like food. And I think when we talk about, so, what Dr. Rubin was talking about with hydrolysine, blood pressure medicine that we use in the ICU. But if you think about timing, we've used timing of therapy for a long time. Melatonin is a prime example. Everyone knows melatonin, right? Probably everyone has had that. Melatonin is sometimes a helpful medication, but many times it doesn't work for people. And in fact, the time that you administer melatonin in a sleep and circadian clinic is crucial, because if you don't give it at the right time to the individual's circadian clock, it doesn't help. It's a waste of money. And so there's this constant battle between what we call process E and process S. So process S is sleep. And so there are other parts of our brain that drive our sleep and parts of our brain that drive circadian clock. And they have to basically align at the right time for us to fall asleep. So this is a very complex sort of neuroanatomic slide that I'm going to skip. But the important thing is that when in a circadian, like we treat sleep disorders, in order to help someone sleep, we have to know what their internal clock is doing, so that we administer either light therapy, for example, or melatonin to actually help their sleep disorder. And if you administer light at the wrong time, so for example, if you have a patient who is incredibly phase advanced, they go to bed at 8 p.m. and they get up at 4 a.m. Right? There are different ways to use light therapy to help them become more phase delayed. But if you administer it at the wrong time, you can actually make their sleep disorders significantly worse. So you have to be very careful with these treatments, melatonin and light. Even though it seems very benign, it can actually make sleep disorders a lot worse. I'm sorry, I'm not going to talk about surgery at all today. I am primarily a surgeon, so if anybody has any questions about surgery, ask me later. So melatonin, I think, is a prime example because everyone in here has, many kids are on melatonin, many adults take melatonin. But you have to know how to take melatonin for it to actually be effective. Otherwise, it doesn't do anything. It doesn't make you tired. In fact, it might have the opposite effect. Is it common here that kids may get Benadryl to sleep and histamine? Anybody know? Maybe you know. Do kids get antihistamines, Benadryl? What's the word for Benadryl? Benadryl. So if you get Benadryl at the right time, it can make you very tired. Anybody that's had allergies to Benadryl knows it can make you sleepy. Like kids, it's very common that if you get the Benadryl, parents will say, my kid is crazy. They were bouncing off the wall, they didn't go to bed at all. And they say, my Benadryl has the opposite effect on my kid. Not true. The problem is the time that they gave Benadryl to their kid. They probably gave Benadryl very early in the night, thinking that it was going to knock their kid out and make them sleep. But because it wasn't lined up with when melatonin was starting to rise, they fought through that fog, that feeling tired. And kids, actually, one of the things that they do when they're tired is they get hyperactive. So they became hyperactive because they were trying not to fall asleep. So again, it's one of the, Benadryl is the most commonly prescribed sleep aid in the United States. Benadryl. I don't like it at all, but most of my patients are on Benadryl, not from me, but from other people, sometimes their parents. So someone asked a question, do we know whether or not the 4 a.m. and the 4 p.m. is aligned with the sort of chrono, like the time, what the individual person is? The answer is no. There are different ways to look at an endogenous circadian rhythm. So everybody probably now has an Apple Watch that tracks motion and sleep. Anybody have one of these watches? I have one. I don't wear it at all. So, but in the clinic, in a sleep clinic, we have things like sleep logs. We ask people, what time do you go to bed? What time do you wake up? We use actigraphy. It's a watch that has accelerometers and gyrometers. It tracks motion. And we have one in particular that also uses core body temperature. So we get an idea of when people fall asleep and when they wake up. And that's how we figure out what someone's internal time is. But that's not great, right? That's not measuring what our molecular clock is doing. So you can do dim light melatonin onset. Anybody heard of dim light melatonin onset? So it's very difficult to do this in the hospital, or even as an outpatient. You have to take saliva and measure melatonin, and you typically do it every 30 minutes. I don't know if anybody has a 5-year-old or a 6-year-old, but trying to wrangle a 6-year-old to take saliva spit every 30 minutes is a chore. So there are other things that we can do, and this is an example of an actigraph that just measures motion. So if you look on the slide, the black lines are motion, and the green is what the device is predicting is sleep. So we use this all the time. Every patient that comes through our sleep clinic gets an actigraph, so we know what their sleep is. But again, these don't necessarily represent what your internal clock is doing. And so there are other ways like DILMO, and even measuring components of melatonin, sulfametoxy, melatonin from urine, but it's not great. And so one of the things that people in John's lab, for example, have been interested in are how can we take different ideas from the circadian biology lab and use it clinically. So This is a paper that Dr. Wu, who's one of John's other postdocs, had published, where we basically took a skin biopsy, so a single biopsy from the skin, and looked at expression of genes, and we were able to basically find what we think the person's internal time is. So rather than doing actigraphy, and rather than doing, for example, sleep diaries or questionnaires, we could take a very small piece of skin and actually get that information. So that's one example of something that we're using in the lab, but hopefully, eventually applying to patients. Diagnostic tests, I think, are another example. So in the hospital, if we have patients that have epilepsy seizures, if they have hearing loss, especially congenital hearing loss if they're born, and we know that they don't hear. If we have children that may have a genetic syndrome, we have panels, gene panels, where we can take blood and actually look specifically for mutations that lead to seizures, hearing loss, genetic syndromes. And so we actually took the same approach in the lab. Y.Y. Lee, one of John's graduate students, actually used machine learning to try to predict what a sleep gene is. Because we know what the core clocks are, but there are many other sort of genes that are expressed in proteins that are made that control how we sleep, the time we go to bed, the time we wake up. And so working with the team in human genetics, we actually took this information from the lab and created a sleep gene panel. And so this panel in particular looks for mutations in what we think are genes that lead to sleep profiles. And so by doing this, we now have this, it's orderable, it's a diagnostic test like getting a creatinine or a glucose. You can actually order this gene panel on a patient and have a gene panel tested if we can identify mutations that cause, we think, different sleep disorders. So we're using this now in our hospital, and hopefully we would like to think that eventually other hospitals will use it. So drug timing is, I think, these are examples where in the sleep medicine field, timing is critical. We already know it. We've known it for a long time. We use timing every day. When we talk about light therapy or melatonin, or even something as looking at sleep genes. But this field of circadian biology is applicable to a lot of different divisions in medicine. It's not just limited to sleep medicine, right? So I think the prime example was, Dr. Rubin's sort of example of how drug timing can be so critical. I like this slide because this was published in 2015, and it was a study looking basically the synopsis, and the synopsis was looking at how imprecise the way that we prescribe medicines are. So in looking at the people on the screen, the blue person is representative of the number of people that actually respond to the medications that are prescribed, and the red people are the ones that basically don't respond to medicines. And what it tells you very generally is that most of the people that get these medications, Crestor, Humira, Abilify, these are medications for reflux, cholesterol, anti-inflammatories, mental health issues. Most people don't respond to the medication. So, is it a question of it's the wrong medication for the wrong patient, or could it also be that we're not prescribing the medications at the right time? Because we now are starting to get an understanding that many medications probably work better physiologically if you time it appropriately. But we don't understand it because we're not doing trials. As was mentioned earlier, it's very expensive to run a clinical trial where you test multiple times a day. And the reality is that's not what pharmaceutical companies have started doing with these drugs. Like they're just testing it compared to a placebo doing but it hasn't been effect. But the more we understand, I think the concept of circadian medicine is we're very early, we're in the infancy of this field, it's going to be, I think, eventually. So most drugs that are prescribed in the US that are FDA approved do not consider timing. There was a question about the FDA. The reality is timing has not been something that's been incorporated. And even if you look at clinical trials, this was the number of clinical trials that started using timing, meaning if you look back in history at the number of clinical trials that started using different times of day to see if the medication work, this was not from the 30s or the 40s. This really started in the 60s. And there have been a bunch in the early 2000s, 2010s. But most of these studies were actually only 2 times, not 3 times a day, or 4 times a day, or probably even 6 times a day. So we don't test these medications at multiple times to see what the effect is. But again, they're in different fields. For example, this is a slide from a chapter that we wrote about treatments of neurologic disorders, and especially mental health disorders. There are medications that we know that need to be given for your treatment, like methylphenidate, for example. If you give methylphenidate at night, it will cause sleep disruption. Dr. Rubin had mentioned Simvastatin. Actually printed on the box by the FDA. That's one of, I think, 7 medications now, maybe 7 medications out of 3,500, 4,000. Don't worry so much about on the slide, but chemotherapeutics is another prime example. There is more data coming out now about the time that cancer therapy is administered. And if you administer it at certain times, it can actually improve outcomes. Some of it has nothing to do with the time that it's given. It has to do with the fact that your body metabolizes drugs differently at specific times of the day. So if you give a medication at a specific time, like maybe in the morning versus the afternoon, you might actually better tolerate the medication because you metabolize it faster or differently. And then you actually can you stay in the treatment therapy longer, right? Many people that get cancer treatment simply don't finish the treatment course because of the side effect profile. So a lot of these studies are looking at side effect profiles when you give it. And now, especially in the circadian biology world, there are studies coming out that show that the way that men and women respond to the timing of medication is different. So we can't assume that treatment for one person is the same as it is for the other person. Again, there are lots of things that factor into this. So I want to sort of skip to hydralazine because I want to talk about this study that Dr. Wolf mentioned. Because I think people talk more about the molecular biology. You know, there are enzymes in our body that fluctuate throughout the day, and that's what metabolizes hydralazine, and that's why hydralazine can have a good impact. But there was a huge sort of clinical implication with looking at the daily rhythms of hydralazine. So basically, anybody that works in the hospital, I doubt that it's different. We've actually compared the way that we treat patients here compared to some other places in Europe and Canada. And what we know is that we come into the hospital as a team in the morning and we round on patients. We make sure that we understand what's happened over the last 24 hours, and then we come up with a plan for the day. Anybody here in medicine? Like, what is rounding like here? Is it similar? In the ICU, for example, teams come in first thing in the morning, and they look at blood pressure and heart rate and body temperature. The same, right? History of medicine. And so decisions that are made, for example, like let's say a patient in the ICU had a blood pressure peak at 3 o'clock in the morning. But there was one intern, one early doctor who was there overnight, and maybe they didn't want to necessarily prescribe a medication, but they said, I'm going to wait 2 or 3 hours for the team to get here, because then we'll decide as a group what we should do for the patients. But by waiting, we administer the medication 3 or 4 or 5 hours later, and it wasn't necessarily the time that the person would have had a better response to the therapy. We don't think about those things at all, and I'm not saying that we do either. We don't. In fact, I will tell you that as we talk about this with the hospital system, sometimes there's pushback. Like, well, how would you change the time that you want on patients? You can't change it. It's very difficult. But I think the reality is the more we learn about some of these medications, the more we realize that the time that you give these medications could be better or worse depending on the time that you give it. So I think the more information we get, the more we realize that maybe we can actually modify the way that we treat patients to think about the time, just like we do in sleep medicine. Like, I'm very thoughtful about the time that I give melatonin or light therapy or any other medication for sleep, Ambien, Lumesta, Balsamra, whatever. And the reality is in this study, Dr. Rubin had mentioned this briefly, but it wasn't just hydralazine. We look at hundreds of thousands of doses, 10 different categories of medications. Pain relievers was a prime example. We don't get pain relievers at the time that we know pain peaks. In many sort of states and many diseases, we know that pain is actually worse at night. But if you look at the way that we prescribe pain medicine in the hospital, pain medicine is actually most prescribed during rounds, either in the morning or the afternoon. But there's a huge lull, a drop in the amount of pain medicine that's given at night, even though in many patients we know the pain gets worse at night. So things to think about. Infection is another prime example. We don't time infection like the timing that we give antibiotics necessarily, because all infections are the same. But there is some data to suggest that the time to administer antibiotics could be better. It could even have something to do with the way that it's metabolized in the liver or the kidney, for example. And I think this, basically what this slide showed is that the red shows the time that the patients that we tested were least responsive to hydralazine, and the blue dot shows the time that they're the most responsive. But the peak, basically, for the time that hydralazine was given, was at the time, exactly the time that they have the least best response, right? But as Dr. Rubin said, just because we know that there's a difference in blood pressure, it doesn't necessarily mean that there's a difference in outcome. So if you time the medication appropriately, what does that mean for the patient? Do they get better faster? Do they leave the hospital faster? We don't know. And so I think, you know, how do we, like 5 minutes left? Yeah. So in Cincinnati Children's, for example, because this, you know, one of the things that we're interested in is collaborating with different institutions, locally, nationally, internationally. How can we design these practices in the hospital, right? So I'll talk a little bit about how we have lighting, sort of, you know, floors that are aware of natural light, not synthetic light. How we can potentially change operational procedures for patients. So this was something that Richard Lang and Jim Greenberg, who were also with Cincinnati Children's, worked on quite a bit. Dr. Hoganesh was part of it. Changing the way that we have lighting in the floors. So I think a prime example is the pediatric ICU or the NICU. The NICU always has light in it to some degree. There's always a little bit of noise, always a little bit of light. Even though we try to keep it calm at night, there are stimuli. And especially for newborn babies, they're trying to establish a rhythm when they fall asleep, when they wake up. And the fact that they're in a sort of a synthetic environment and we don't control it means that it probably takes them longer to reach that steady state of sleep, right? But the hospital system that we have has test beds where there's actually a sensor on the outside, basically, that tests what the wavelengths are that. So if it's a sunny day, it replicates those wavelengths in the room. If it's a cloudy day, it replicates those wavelengths in the room. And then we compare it to the other type of synthetic environment that we have. And the hope would be to look at outcomes like a kid that had surgery or a kid that's on medication. What does it mean to have natural light versus synthetic light? Does it mean that they have a quicker recovery? Does it mean they get out of the hospital faster? And I think that there are some diseases where it may matter, but there are many diseases where it doesn't. So it's just as important for us to understand when timing does not matter. Right? Negative data is useful data in circadian biology. I stand by that statement. This was a picture of the Alfred ICU in Melbourne, Australia. I think that this was a good representation of a hospital that tried to incorporate natural light for patients. The cardiac ICU, this is a particular interest because there's a lot of data now that shows that for patients that have just undergone heart surgery, if they have disturbances at night, if it's loud or if it's highly lit, these patients are more likely to have negative cardiovascular outcomes in the hospital. But if we can control it so that they get good sleep, they actually have a better outcome. I mean, if you think about it, all we're really talking about is trying to get patients to have good sleep in the hospital. Something that simple is an easy place to start. I think it can be a lot more complex, but that's something that we can talk about. So this is another example of a study that we set up with the bone marrow transplant team. We have a very large bone marrow transplant group in Cincinnati Children's. We've worked with phenomenal clinicians and researchers, Stella Davies, and Michelle Wang. And these patients come in for a bone marrow transplant. They're admitted for many weeks, sometimes months. They're often on feeds, TPN, for example, that doesn't necessarily replicate oral feeds. And so they might get feeding around the clock, 24 hours or 22 hours. And so we actually met this group and went into one of the rooms, and they're darkly lit. They have different feeding time. These patients often sleep during the day and up at night. But these are patients that just underwent a bone marrow transplant. So this is a very significant hit to their immune system. And we know now that our immune systems function with circadian rhythmicity, right? So when lymphocytes move into lymph nodes fluctuate throughout the day, our immune system, there's some data that suggests that timing of vaccines, for example, is better. I think that that's still early in the game, but that's what the preliminary data would tell us. And so we talked to this group about doing something as simple as trying to improve the way that we either administer feeds or allow them to sleep. And so this data is about to be published, but the broad overview is that we took patients and the dietitians were fantastic. They were able to create feeds so that we could either feed them only during the 12-hour day versus the group that's getting these feeds overnight. Super simple. Nothing else changed about their care in the hospital. And what we found was that they basically transitioned from TPN to PO feeds about a week earlier. That translates to getting out of the hospital probably 7 days earlier, give or take. And so if you imagine every patient that's admitted, they transition to PO feeds, so we're not paying for TPN, and they get out of the hospital faster. That's hugely impactful. And of course, we're also interested in things like blood pressure, for example. So we know that if you take healthy adolescents and you feed them at night instead of during the day, you can create blood pressure problems and pre-diabetes, metabolic problems. So we actually are looking at other things like their immune function and how well we can control blood pressure problems in these patients. So we're looking at a lot of other this is early data. And then I guess the ultimate goal is to do this, which is to create the Center for Circadian Medicine. There are several adult centers in the United States. I guess we would argue that ours is maybe the first one in the Children's Hospital, but we modeled it after other circadian biologists that developed these centers at other institutions like Northwestern and Harvard. And I think that trying to figure out ways to bridge this gap between the research that happens in a lab and the way that we treat patients is the goal. Because, and interestingly, in sleep medicine and circadian biology, there are two very different fields, but with a very common theme. And so I think that what we're trying to do is take some of these ideas from the lab and apply them to patient care, because I do think that we can make some of these therapies better for patients. I mentioned this because I put this in a lot of talks now. Everyone know what obstructive sleep apnea is? No one likes questions. Sleep apnea, super common. There are more than 1 billion people worldwide that have sleep apnea between the ages of 30 and 69. So super common. I treat a lot of kids with sleep apnea. This was a study that was done in Europe that looked at the cardiovascular outcomes for patients that either had sleep apnea, shift work, or short sleep duration. And then basically the ones that had 2 of those or all 3 of them. And the reason I think it's important is because what this slide shows, the take home from this is that if you have short sleep duration, or let's say poor quality sleep, and you compare cardiovascular outcomes to a patient with untreated sleep apnea, the risks for cardiovascular outcomes, heart attacks, myocardial infarction, strokes, is equivalent if you have poor quality sleep compared to patients that have untreated sleep apnea. So we think about all these diseases as bad things happen because of the disease itself. But in reality, there are lots of diseases where bad sleep is part of it. Look at dementia, Alzheimer's, for example, Parkinson's. There are sleep disruptions that happen many times decades before the neurocognitive dysfunction happens. And so there are some diseases where we see sleep disorders well before they ever develop neurocognitive dysfunction. right? Like REM sleep behavior disorder is a prime example. But sleep disruption in and of itself actually can lead to a lot of bad outcomes. Cardiovascular is one example. So I think as we move through this, having respect for good quality sleep, it's funny because it's in the news now all the time. Sleep is important. Well, I think we've known this for millions of years, but now it's really important in the last 10 years. But it is. And so I think even as a surgeon, I think about the quality sleep that my patients get after surgery on the floor, because I know that it can potentially impact how quickly they recover and how quickly they leave the hospital. And we have obviously a lot of collaborators, and the goal is to take these concepts in circadian biology and apply it to different divisions, different divisions in the hospital. That is basically it. Thank you.
Vamos pegar a plateia presente. Amém.
I would like to know about what's your opinion on the connection to microbiome, these biologists and circadian sleep. What's your opinion? What's your opinion on these biologists and circadian sleep? Sua opinião.
Yeah. So he is asking if there's a correlation between the microbiome and diseases. So this is actually a great question. So the short answer is that even the bacteria in your gut have their own clock. And in a steady state in healthy patients, we think the microbiome clock is aligned with our clock, generally speaking. And there is a lot of research. We have collaborators, for example, in Philadelphia that are interested in looking at the microbiome in the gut in diseases like inflammatory bowel disease, because there is data now to say that when the microbiota changes or when their clock changes, that could potentially have an impact on diseases. Not necessarily developing a disease, but maybe when you have flare-ups of irritable bowel syndrome or inflammatory bowel disease. So I definitely think that there is developing information in that field. I think that it seems like it's going to be of big interest. But I think that, and I'm obviously not the expert on the microbiota clock, so I'm trying to be general because I don't want to say something incorrect. But the short answer is yes, I do think that there is correlation between the bacteria that live in your gut and their internal clock and our internal clocks and how they work together. And for sure, physiologically. And I think that there's data now to suggest that it could have relevance in things like inflammatory bowel disease. This is an example.
You just turn on, turn off.
It's on board. Well, I'm ready.
Parabéns, é admirável o trabalho de vocês. E uma das coisas que a gente vem acompanhando é essa modulação que tem feito no hospital em relação à luz. Vocês implementaram isso na unidade neonatal e já tem feito isso em outras unidades do hospital também. E se já tem algum resultado preliminar?
First, congratulations for the presentation. And the question is if you have implemented the lighting control of in the NICU environment. I know you have this in the NICU, right? And if you have preliminary results on this controlling environment, I think that's the question. The impact of this in the babies.
Great question. So that is an ongoing study right now. So we actually have portable units to change the lighting for in some rooms, but also portable units so that we can take them from different areas, not just the NICU. but that's an ongoing study. And I think the hard part about that is that those studies will take a while, because in the end, what we have to do is pick patients very selectively so that they have the same disease. The NICU is obviously full of kids that have different things. And so I think to compare outcomes and lighting, you have to very carefully select very homogeneous populations. So I don't have preliminary data for this talk, but that's something obviously that the groups are working on at Cincinnati Children's.
Em português mesmo, para ser mais prático. A respeito da influência sazonal, e se eles levaram em consideração esse experimento de controle, na aplicação, né, dos leitos.
The question is about seasonality, basically, and if you control the change that happens throughout the year, if you can model these effects, like alterations throughout the year related to seasons.
So that is a crucially important question. Generally speaking, I only speak generally. I have no details. Generally speaking, the interesting thing about, we were talking about this at lunch, seasonality. I think a lot of the early work assumed that seasonality was very much dictated by light, right? Light and body temperature. I think there is data now to show that it's not always about light. Your body actually physiologically makes changes before we see some of those dramatic shifts in light and body temperature in preparation for changes in seasonality. Well, that's not true for everything. But I think that in order to truly discern changes in seasonality and impact on disease, like mental health, for example, because that's a big, you have to control for things like lighting, temperature. Otherwise, you can't tell what is internal physiological changes versus what is purely influenced by an external factor. So, and that's very difficult, right? Because people that study seasonality, Dr. Rubin made this point earlier. I study sleep apnea, so if you take a mouse, you have to expose them to hypoxia for 3 months. Not a lot of people want to do that. You have to really be passionate about it. And I think seasonality is the same. To study seasonality in its truest form, even if you did it in animal models, it's a huge time commitment. So it's very difficult to run those studies, but it's absolutely critical. I know that there are groups that are doing this, but I don't think that they're in the front.
Ok. So, mais questões, mais perguntas da plateia? Temos questões do chat. Então, como eu falei, se vocês tiverem, os slides vão ser compartilhados, né? A gente vai ver uma forma de compartilhar os slides para quem estava assistindo, de visualizar. Né? Serão compartilhados por uma. Eu acho que é isso, né? Agradecer a presença de vocês. Tem um tempo também um pouco corrido, a gente tem uma reunião na sequência, mas foi um momento dentro de um contexto de colaboração que está sendo trabalhada, né, com o grupo de lá. A gente tem esse momento aqui para discutir um pouco sobre a relevância de relógios biológicos e síntese e reação. I'd like to thank our vital researchers, and it's very good to have you here in our hospital. E final, se não, a gente encerra por aqui o seminário e agradeço novamente a presença de todos. Joia?